My name is Takahiro Sayama, and I'm professor at this PBRI, particularly focusing on flood disasters. And my major is hydrology and focusing on floods. And today the plan is that you stay here in this room for all day. Today I will give my lecture and the introduction of DPRI briefly from 10 to 11. And then maybe you can take about 15 minutes break. Then followed by we have my colleague, Assistant Professor Koda Yamamoto, will give a lecture till 12 o'clock. Then maybe you can have a lunch break till around 1 o'clock. Then Professor Wu from actually Taiwan originally, and he's also the associate professor at DPRI, will give us a lecture, will give you a lecture for about 1 hour. Then followed by my lab, we have assistant professor, and he will give Sugawara, he will give about 45 minutes kind of our research introductions too. So that's going to be like four people, professors, lectures. And then you will have Sugawara will accompany you to bring you to the museum. Not necessarily like a big museum, of course, but in DPRI we have some exhibitions of our facilities. So you can enjoy. And that's the whole plan. And then maybe tomorrow and the day after tomorrow we will stay in the Ujigawa Open Laboratory accompanied by Professor Kawaike. So the DPRI, you went to Yoshida campus already?
Yes.
Yeah, you went to Yoshida campus. So we have 3 campuses, and the Uji is located kind of southern east part of Kyoto. And this is a kind of easy access to Kyoto Station. Do you stay in Kyoto Station, nearby Kyoto Station?
Yeah.
Yeah. So it's a very convenient place. And then after this, I will go to Katsura campus, because the graduate school of engineering now moves from main campus to Katsura campus. So I will drive my car to go to there to give my lecture for the graduate school. So the main campus undergrad basically here, and then the DPRI and the other research institutes we have, including chemistry, for example. We have 4 research institutes in Uji campus. And also, you can see that, yes. So our DPRI located nearby the Obaku station. It's good that most of you can read kanji characters. And then if you go to Chushojima station, there is an open here along the Ujigawa River. We have an open laboratory, and that's the Professor Kawaike's research institute, not institute, I mean the laboratory under DPRI. So I think you came from this main entrance of DPRI, and then you found this room. And my lab is somewhere here, besides this cherry blossom. And Uji campus is a very big area, and so you came from here. Then we are somewhere here, and then the museum, as far as I remember, it's somewhere here, so it's quite a distance. And then around here there is a river. Yeah. This is not our place. It's
school.
School, yeah, elementary school. And then also we have a self-military defense in the Obaku. So you can see that it's a very large area. And the DPRI started 1951, so we have quite long history. And especially after the World War II, there are a lot of natural disasters, including floods, storms, earthquakes, and so on. So the DPRI, the Kyoto University, decided to create the research institute for focusing on the disasters. And of course, it includes geophysics, geology, civil engineering, agriculture, and civil engineering, agriculture, civil engineering. They are the kind of members. So you can see that the different disciplines. I'm civil engineer, but there are different experts started to create the DPRI. And currently, for example, myself belongs to graduate school of engineering, but also some of them are informatics, and some of them are focusing on the science field. So that's a unique part. And about 100 the faculty members, about 33, 4 professors, about the same number of associate professors, and the rest are assistant professors. And then, of course, there are many researchers and so on. And the DPRI has about four groups. And I myself belongs to Integrated Arts and Science for Safe Reduction Research Group, even though I myself is more on the water related. And many of my colleagues from water belong to atmosphere, hydrosphere research groups. And then geohazards, and then of course the seismic and volcanic hazards. This group is kind of unique that we focus on more on the society and also a kind of integrated multi-hazard issues. So, for example, one of my colleagues from this our group conducts, for example, the training for the disaster, like disaster drills. And also, this is activity by the seismic group, so I will skip for this time being due to the time. And also for the atmospheric group, and myself also very much involved in climate change studies, of course. So we have the impact assessment of the climate change, and again, they're focusing on the natural disasters, in particular floods, storm surge, winds, and so on. And then we also have a number of the memorandum of understandings, MOU, and that includes the your university DPRI. Yeah. So yes. Yeah. And then the other uniqueness of this DPRI there are many kind of on-site facilities within Japan. And also we started recently outside of Japan in Mexico. But they are kind of observatories for the different objectives of the research. And then you visit this open lab for the hydraulics. Okay, so that's about the DPRI. And and also, I'm sorry, maybe I can give you these slides to you. Sorry, quick. But also we also have the master's student and the grad students, and they belong to for example, my lab students belong to Graduate School of Engineering, but then their lab is in DPRI. Myself belongs to DPRI, but of course I'm at Kyoto University. So that's the kind of structures. We also have undergrad students also. Okay, so that's about the DPRI introductions. I don't think that you have any questions on this one. So let me skip start my lecture. So today, as I said, I myself hydrology. So I focus on so-called rainfall runoff processes. But also I've been working on the floods, so the inundation is very important. So the rainfall runoff models, have you heard about rainfall runoff models? Co-induced models. And combined with these inundations, and that is the model that I've been developing, and so I'd like to introduce our modeling. And also, I'd like to talk about the applications for flood forecasting and climate change, particular risk assessment. That is my today's 1 hour, about 50 minutes lecture. So you can see that this is the graph of the number of the flood disaster. This one is the loss, death and missing on the orange color. And then on the right hand side, this is the economic damage with the blue losses by the floods in Japan. Is that the same maybe in Taiwan? I think it's general that around the 1950s we have a lot of disasters, and then we kind of successfully reduce the number of the deaths. You can see that this is a logarithm, log scale, so it's quite a lot significantly reduced, because previously we have disasters, killed about 1,000 people by a single event, but then now we don't see such kind of disasters, of course. However, the economic losses, of course, has been reduced, we thought, but then nowadays, especially I would say about 2015 till now, last 10 years, we have quite significant disasters, very large-scale ones. And then economic losses also, some of them are very significant. One of the surprising ones to me also was the Kinu River flood in 2015. But the reason why it's surprising to me, I studied about these flood issues since 2000, around 2000. But then there was no this kind of significant flood events in Japan. This means you can see that this is the embankment, and then embankment breached. And then you can see that there are lots of water, massive water from this Kinu River to the floodplains. So this is a kind of typical flood disasters. You can see that the ladies was breached, and then the floodplains. And about 40 square kilometers of the area was flood inundated. And I would say this is a kind of typical flood issues that we try to avoid. And then we thought that it's been successfully done when I started my research in 2000, right? It's not in 1950s. So, however, and then we thought that only the remaining issues were kind of small-scale disasters. However, oh no, this is not true. In 2015, this kind of mega disaster, flood disasters occurred in the urban areas. And then many people were actually rescued by the helicopters, and there are obviously lots of housing damages. And also, in terms of the mountainous areas or the small rivers, we thought that this kind of course, disasters occurred, but then this was very special in northern Kyushu 2017, in the sense that there are massive landslide occurs. You have the same issues too in Taiwan. And then there was a lot of landslides, and then the landslides actually deposit. There are debris flows, and then the sediment deposited, and because of this one, there is no room for rivers, stormwater to flow. So that's why the flood inundation occurred. This kind of significant disaster occurred also in 2017. And of course, if I take this kind of example, there are even many more, but then I will skip this introductions of the typical floods in Japan. However, so we have this kind of disasters occurred very frequently nowadays. And basically, we have, for thinking about the countermeasures, we have to do, of course, the hard measures, but also in terms of soft measures, we have two kind of approaches we can think of. The one is the flood forecasting, kind of real-time forecasting. And then the other one is a kind of flood hazard mapping or river planning and risk assessment, and of course, this is for designing. Then, of course, the constructions of the embankments and other countermeasures, or maybe the dams. So you can see that two things. And then my point is that for both objectives, rainfall runoff modeling or our simulations that we are going to talk about is very, very important. Methodology is very important for two of the objectives. Even though they look a bit different. One side, this one is more for the river planning. So typically what we do is how much flood can happen once over 100 years, for example. Whereas this one is what is going to happen in the coming few hours. Real-time planning. They are different objectives. However, we still need to somehow predict what's going to happen. That is a typical case. This is, I usually add this slide to ask you. I think up to now, you understand why flood forecasting is needed. But then maybe I can ask you, so how do you think, in your Taiwan major rivers, I suppose you have this kind of criteria?
Yes.
Right? You have this?
Yes.
Yeah. And do you do flood forecasting on the real time?
Yes.
So maybe the question that I sometimes to ask to you is that why in addition to observe water level, monitoring the water level, why do we need flood forecasting? Because now, for example, if the water level reaches to here, then we give warnings, right, to the residents.
Yes.
So why do we need to forecast in advance? Forecasting.
It's for predict what happened next.
Yeah, that's right. So it's a simple question. So of course, in addition to monitor the water level, we'd like to know what is happening in few hours ahead or maybe few days ahead. That is forecasting. And indeed, in Japan, I'm not exactly sure about Taiwanese case, we have a kind of combine these two things together. So that means once the water level reaches to, for example, this one, and then if this water level is expected to project or predicted to reach to this level in, for example, 3 hours or something, then this warning will give this one, or something like this. So there are a couple of rules depending on the conditions. But then my point is that forecasting is actually conducted, and then kind of not just the forecasting by the government, but then the forecasting informations are kind of included in the system to give the warnings for better evacuations of the residents. So to do so, we have basically these landscapes are very much similar between Taiwan and Japan. So we have very much mountainous areas. Of course, as you see, there are some houses in the upstreams. But then mainly our residential areas are kind of located in the downstreams. And then most of the cases that we have the embankments. And then if the embankments is breached, then flood inundation occurs. This is a very typical settlements. And then related to this topic, the items, there are a couple of important variables that include precipitations, of course, and then the river discharge, and then water levels along this river. Then once if the breaching occurs, then how much inundation spread it. So these four, precipitations, river discharge, water level in the rivers, and then inundation, they are kind of key four important variables. And in terms of modeling, there are different kinds of models we use. And one, starting from the top, so for example, numerical weather prediction models. Have you heard about this one? So it's a kind of weather forecasting. But then weather forecasting is not just like, oh, tomorrow is rain, so tomorrow is sunshine. But then we would like to know how much actually rain falls, like 30 millimeter per hour, 100 millimeter per hour. This is what we would like to know. But then if you can do so, we can maybe use our hydrologic model, rainfall runoff model, and then we input observed rainfall by the radar, for example, and also forecasted rainfall gives to rainfall runoff model. Rainfall runoff model means from mountainous areas to river, right? So the river discharge, so-called hydrograph, can be calculated. Then we use this as a boundary conditions of the kind of upstream areas. And then I think you are familiar with hydraulics, and then you can do, for example, river routings as open channel hydraulics. Then you know water level distributions along this river, so we know where is the dangerous and so on, and also how flood water propagates from upstream to the downstream. Then once the breaches, then this inundation model can be used. Typical ones. And in terms of real-time forecastings, typically what kind of models are used? How do you think? Let's say I said that there are basically two applications, right? And one is the real-time, the other one is the plannings. Let's focus first on this one. For this forecasting, which models? Of course, there are 4 models, so 4 kinds of models. Everything are important. But then let's try to think about the priority. Which one do you think the most important? Which one? This one? Yeah. This is very important. Second one, this one. I would say that this second one is important, in particular for the real-time forecastings. It is because what happens is, or in other words, even if there is no forecasting of the precipitations, we can still do flood forecasting. That has been done before. What does it mean? Suppose this basin, river basin, is fairly large, that precipitated water travels from upstream to the downstream. Of course, we are not like US continental countries, but then still takes, say, 6 hours, for example, to reach to here. Now, we have radar systems, we have the telemetry, the rainfall gauges. So if the rain gauges measures the rainfall, very severe storm in the upstream, we can run the rainfall runoff model on the real time. Right? Then we know before the water comes, we know the discharge, how much discharge appears in the downstream. So even without the numerical weather forecasting, or in other words, even if there are some errors in the weather forecasting, based on the observed records, utilizing kind of so we call the flood travel time or flood concentration, time of concentrations. There are a couple of words used here. But then say time of concentrations means the time to water comes to here. We can utilize this time for the real-time forecastings. And previously, there was no real-time kind of river routing systems, as it was a little bit computationally heavy. However, nowadays this can be simulated very quickly. One thing that has not been realized yet, at least in Japan, I know in Taiwan there are some attempts, and of course in Japan also there are some attempts. But the inundation, real-time inundation simulations has been a little bit challenging. It is because we do not know exactly when and where this breaching occurs. This is a very chaotic phenomena that it's very, we know discharge, but then we don't know where actually levee breach occurs. This means we don't know exactly how inundation occurs. So that's why the reason why we actually utilize hazard map. You know hazard map?
Yes.
Hazard map means that we kind of breach the embankments at the different locations to calculate the flood inundations in advance. So we know that if discharge occurs, this kind of discharge occurs, we don't know exactly where this happens. But then we kind of simulate it in advance and then overlay of those inundation areas to estimate kind of dangerous areas. So for the residents' point of view, we know if flood occurs, where is dangerous. That is at least the Japanese way to do. So it's a kind of real-time ones, and then kind of planning or hazard mapping are both like important, both sides of the coins. Now I will focus more on the rainfall runoff part today. And in terms of rainfall runoff, this is a very typical hydrologic cycle that I don't need to explain, I think, to you. But then we are focusing on the rainfall and then how much water goes to the river. And then through this system, of course, we have to think about very carefully how much water flows inside this soil layer. I can spend about 1 hour or so to explain about the details of hydrologic processes. But then, because today 1 hour lecture, so I will skip. This is only the summary. And if you are interested in, sorry, I didn't put the citations. But this is a very typical diagram to kind of understand, classify, so-called the Dunn graph, I think, by the Professor Tom Dunn first kind of illustrated this one. But then important part is that depending on the, for example, climate conditions, depending on the topography and soil conditions, dominant runoff processes are different. In other words, modeling, we have to somehow represent those dominant processes based on our understandings. So I think you can easily imagine that in the climate, very like dry areas, like a desert, then what happens if there is a very severe rainfall, there are flash floods, right? And that when the flash flood occurs, even though the soil is still dry, because of very heavy rainfall, so infiltration, excess overrun flow occurs. That's called Hortonian overrun flow. Whereas in the humid areas, typically the water actually, precipitated water flows into the soil. But then depending on the topography, for example, in the very steep topography, typically this subsurface, so-called subsurface water is very important, dominant, even during the floods. So this is a very typical cases in Japan, and I suppose the same in Taiwan. So that means if you go to the mountainous areas, for example, there are 1 meters or 1.5 meters soil. Below the soil, do you know what's below the soil? So you see the mountains, you see some soils on top, very steep forest. What happens in below, say 1 meter, 2 meters? Clay. Like a kind of bedrock, like a rock exists. Depending on the rock geologic conditions, but typically the rock is, of course, depending on the weathering conditions, this rock is much less infiltrations, like it cannot penetrate the water. So if we have the steep mountains, compared to soil is very permeable, means that the precipitated water can easily go into the soil. But then, because of this interface between bedrock and soil, the water started moving laterally. Laterally means toward the downstream to the hip slope. So that creates the floods. So in Japan, if you go to mountainous areas during the storm events, you don't see very much overland flow, which you see maybe in the dry areas. However, we still have the floods. Right? That means the water actually flows inside the soil very quickly, or maybe somehow pressure propagates too. It's a very complex system that there are many unknown things. And then that's what we have in Japan, in Taiwan. And then in this system, maybe somewhere like the European countries, gentle topography, not like here, and then we don't see clear boundary between bedrock and soil, then what happens is that precipitated water will go to groundwater. And then the groundwater has some sort of hydraulic gradient. So this groundwater also moves gradually to the rivers. And then sometimes because topography is gentle, so overland flow occurs because of the groundwater returns to the surface. So you can see that there are, of course there are many other complex systems, but then depending on the conditions, this we can fairly easy, how can I say, classify in this manner. Now, in terms of the modeling of these hydrologic processes, the objective of this modeling is that we would like to simulate rainfall to the river discharge. Traditionally, we have very simple so-called tank model, for example. That means we make the catchment, the river basin, so catchment, as a single unit. In this case, we have 3 kind of vertically connected units to simulate rainfall runoff. For example, let's say this is the surface layer, this is subsurface layer, this is the deep groundwater layer, for example. Then we decide the parameters to simulate from rainfall to the discharge. This one fairly works well, so it's being used a lot for hydrology. Maybe there are different versions of this one, but then in general, it's so-called bucket type model has been used. In Japan also, even simplified version of this one by excluding this one. So we have only a single bucket type of model. This one also works very well. So in this storage function model, unlike the tank model, we have this one is a kind of non-linear relationship between storage and discharge. However, you can see this one is, what is this one? This
Discharge.
mass balance, yeah, discharge. This is a discharge, and this is a storage. So the storage changes, DSDT, is the input rainfall minus discharge. So this is a basically mass balance equation only. Well, and then how much discharge goes from storage. So storage and discharge relationship. That's it. So this is a very typical hydrologic models. And this kind of model has been applied very much in the world, so-called the lumped model. Lumped model because the catchment is kind of lumped together as a single tank or multiple tanks. That's why it's called lumped models. But the problem of this one is that, what is the problem of this? The challenge is here is that there are some parameters. So for example, S and Q, we don't know when there is how much of storage, how much discharge, we don't know. But then we have to have somehow so-called calibrated parameters. Have you heard about calibrations? Yeah, that means that we have a models, but then in order to in order to fit these models to particular basins, we have to decide these parameters. But these parameters should be very different depending on topography, catchment size, geology, climate conditions, etc., etc. So unless we have the very good data between rainfall and discharge, because storage we don't know, so we have to somehow decide, optimize those K and P. That is what has been done in hydrology. That is a bit different from hydraulics. Hydraulics, you do some experiment, for example, and then of course the Manning's roughness is still a kind of empirical parameters, but then there are some physically meanings, right, or explained. So as you go from very typical hydrologic lumped type of models towards more physically based models that I'm going to talk about in hydrology. Hydraulics, typically they use hydraulic model, that is a physically based models already. The parameters that we are going to use are a little bit more representing the natural or hydraulic properties, physical properties. But of course, the hydrologic processes are very complex, as you remember that the water cycle is so complicated that compared to hydraulics, even though we say physically based, nothing can be perfectly physically based. It's still the kind of representations of the natural systems. For instance, you know this one, this is a very typical Manning's equations. Manning's equations, I think you learned first in hydraulics. This is the kind of equations can be used for open channel, right? But then this kind of model has been applied also can be slope. Like, for example, this is a rainfall, mountainous slope. If there is a rainfall, then how much water goes to the river? So we can use that same kind of concept for slope. But if you apply this one to mountainous hill slope that I mentioned, what kind of possibility of wrong? What is problem? If I apply kinematic wave model to, say, Taiwanese mountainous hill slope, slope angle can be somehow estimated by the topography. But then, as I said, in the mountainous area, what is the hydrologic processes? The water goes to the soil, and then they flow inside the soil. So it's very different from this kind of open channel hydraulics, isn't it? So even though this looks like more physically based, when we talk about Manning's roughness, this is a very effective, so-called effective parameters. It's not perfectly the same with the physics. So that's the difference. And then when we apply this one, typically what happens is, because, for example, this is the mountainous hill slope, and then we have some angles like this, and because this goes all the overland flow, so what happens is that the river discharge you observed here is so quick. The reality is maybe a little bit slower than this, because the water flows inside the soil. So such kind of the differences can be occurred, and we would like to improve our models by incorporating actual hydrologic processes. As I said, the lumped model, like storage function model or tank model, is typically consider the storage as a whole. How much water stores in the catchment, how much water comes out. That is storage discharge relationship. Right? But then what we typically use nowadays is so-called the distributed models. Have you heard about the distributed models? I know. Yeah. I think I think you heard about 分布型 Japanese we call Fugata model. And and then that is one different thing is that we actually did consider, for example, flow directions based on the topography, because we know elevations in detail, right? We have a GIS and we have the topographic data, so we can decide the flow directions in advance to make our simulations more physically reasonable. And then we can apply the different kind of, for example, kinematic wave model that I mentioned can be applied to calculate from mountainous areas to the rivers. Then the river, maybe we can apply different equations. For the mountainous areas also, today I'm not going to talk about in detail, but just give you some concepts. For example, one option is that we can apply some Darcy laws, you know the Darcy laws for the soil physics. The water flows inside the groundwater first, then after this overrun flow. So we can maybe combine a couple of different equations to represent the water flows inside soil and then water on the surface as such. So we can improve this kind of processes, more reasonably well representing the actual fields. So today I'm not going to talk about in detail about these equations, but then my point is that having this kind of distributed models, we can represent the processes more reasonably to the actual conditions. So that is this kind of advantage of distributed rainfall models. And previously, maybe back in 20 years ago, when I started my study distributed rainfall models, it has not been very well used in practices. It is more considered as a kind of research models. But then now, because the computational power has been very much improved and nothing is difficult, so more and more people started using distributed models, as far as I understand. So I said the limitations of the lumped models, or in other words, the advantage of distributed models is that, for example, we can reflect the spatial distributions. Spatial distributions means, again, the boom of rainfall. We now have the radar rainfall. We can use that. We know the topographic informations. We can use that. We can also state variables means, for example, water levels here, 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 here are different. So we can use them. And we can also, the other good advantage is that you are interested in the river discharge at this point. That's true for the lumped models. However, as I mentioned earlier, there are many floods in the upstreams too. So we are interested also in the river discharge at this point, this point, this point, this point, this point, this point, this point. So we can look at the inside the basins. That is the other big advantage of distributed rainfall runoff model. So that's why we are focusing on this distributed rainfall runoff models. Now, but then I started the development of this called RRI model about 10 years ago. And I will explain what is the difference between distributed rainfall runoff model, RR model, to this inundation model. So this is the diagram that I mentioned that has been used or implemented in Japan, maybe the same in Taiwan. Means that you can see that this is a lumped model. I actually mean that. Then I have the distributed models in this way. If my objective is just only to estimate the river discharge at this point, then actually this one have actually worked fairly reasonable in a similar way. In other words, I said if I have a good data of the river discharge, I can calibrate the parameters even for the ranked models. Then I get the very good results. This is very typical. So there is not so good big advantage of using this one if I focus only on this one. However, the situations is very much complex compared to this one. When I started this RRI model development, my focus was more in the kind of developing countries and with the large river systems and then a lot of inundations. The typical image of this one, even though Thailand, for example, is no longer developing countries, but in terms of how can I say, hydrologic system, it's very different from Japan. You can see that as this figure shows, for example, Bangkok is located, you know, the Chao Phraya River. Have you heard about Chao Phraya River? Chao Phraya is the Thailand, the very deep river. And Bangkok is located in the downstream of Chao Phraya River. So they are very much keen, important for them to know flood inundations. Unlike maybe Taiwan or Japan, they are very flat area. They are very flat areas in the downstream. So inundations spread very widely. And this inundation cannot be controlled completely. Also, if you are interested in, for example, river discharge at this point, unfortunately, there are even a lot of inundations in the upstream too. So this means this river discharge is very much affected by upstream inundations. So in other words, even if I have distributed models, I would like to estimate the river discharge. That is my mission actually that time when I was working at the different institute, focusing on the kind of disasters in the other countries. Typically, there are many inundations in the upstream. In that case, river discharge cannot be simulated by RR model, rainfall model, because you can see that these structures, the water just goes directly to the river. The reality is that the water actually goes toward different directions. So such kind of things cannot be simulated by the typical rainfall model. And then I thought that, okay, now we should simulate both rainfall runoff and flood inundation together. Otherwise, cannot be done. Cannot be done means cannot simulate the river discharge here. But also, people are interested in flood inundations itself. And flood inundation occurs at different places, not just only here. So in such kind of cases, we propose to simulate both rainfall runoff and flood inundation together on the two-dimensional system and a bit more in hydraulic ways. And that's about 2012, 2015, and I've been working on this one for the last 10 years. So the input is the topography. DM means the digital elevation model, land cover and cross sections, and then we input the rainfall, and then calculate the river discharge, water levels, and inundation together. By doing giving the rainfall, we calculate the same as just the distributed rainfall model from mountainous areas. But then the water comes and then spread it to the floodplains. Then this spread inundated water also returns back to the river discharge, river. So there we consider kind of interactions, flood water and flooding water and river water. So the one main difference between distributed rainfall runoff model and then this, I would say this kind of model, because there are now similar types of models not only RRI, but then this kind of inundation models has been developed. So the one main difference is that typical distributed rainfall model decide the flow directions in advance, and then the water flows to the river. That's why only river discharge can be calculated. Whereas RRI model, this type of model, we track the water levels, and depending on the water levels, of course the water can actually in the different directions. So if you know about flood inundation model, it is a little bit closer to inundation model in the sense that it's a two-dimensional simulations. But then, unlike typical inundation model has been applied for hazard mapping, for example, we can also calculate the rainfall runoff. So we give rainfall as the input, and then calculate the hydrology process inside the soil, and so on. That's the RRI model structures. And in terms of the fundamental equations, I think you know about dynamic wave models. It's a kind of full hydraulic equations. And we have also kinematic wave. And then RRI model decided to use the so-called diffusive wave model. So kind of it's in between dynamic and kinematic. Sorry, if I have time, then I can spend a little bit more time to explain more in detail. But due to the time, let me say we use diffusive wave. That's all for now. And this one also I will skip. Sorry, let me skip about these details. But then RRI model, of course, as I emphasized earlier, depending on the parameter settings, we can consider different hydrologic processes. So, for example, in the urban areas or say concrete kind of hill slope, then we do not need to consider the inundations, infiltrations. But then in, for example, paddy fields or croplands, we may need to consider vertical infiltrations. And then in the mountainous areas, as I said, subsurface flow is very important. So depending on the parameters, we use the different equations. We can actually try to represent a subsurface flow. So that's why the models are a little bit more physically based rather than kind of only use overland flow, for example. So this kind of the arrangement has been done. Okay, so I have about 5 minutes left. So do you have any question up until now? Go ahead, please.
I have some questions. Maybe briefly. The first one is it's a very interesting content, and I just wondering if because we know in environmental modeling we need a lot of monitoring data. So because we need to finish the model calculation and evaluation. But I just wondering, is the data, the environmental data, sufficient in Japan?
Environmental data is also limited, I think, in Japan. Yeah. So, and then my understanding is that even though they monitor, for example, water quality, it's not very much kind of systematically monitored. So the quality of the data quality is not very much maintained well. So my understanding is that such kind of data, of course, for the research purpose, if you focus on particular point, there are some data available. But then, for example, nationwide data sets I don't think that we have good data yet.
Same in Taiwan, we don't have enough monitoring data,
Right.
particularly in water quality.
For the river discharge, we have very good data sets. So nowadays, I didn't have time to explain today, but we apply this kind of model for the entire Japan. And then we try to utilize many gauging stations at once. to calibrate the models. That's the trends now, I think. Yeah.
Maybe one more.
Hi.
Also,
Yeah, that's, yeah.
you suggest this kind of rainbow and roundup model, and this kind of model is all deterministic model.
Deterministic, yeah.
But nowadays sometimes we apply the stochastic model based on big data. This is very different from the deterministic model. So I'm just wondering, have you applied this kind of
Machine learning type of things? Yeah. Yeah, for example, PhD student works on the machine learning recently too. But then I see that the recent trends is that there are this kind of physically based models is there, and then there are many attempts to combine the machine learnings and or maybe, as you say, stochastic models, and then this kind of deterministic model in various ways. For example, calibrating those parameters are very challenging, and then running these simulations quickly is very challenging too. So we call them, for example, emulators. That means the machine learning actually can learn from this deterministic model to represent this one. Yeah. So as such, there are some trials, I think, to combine
so
them.
you can increase the efficiency
Right.
of the model.
Exactly. Yeah. And then try to give the feedback even to the models. That is the concept. I think.
Combine two type of models.
Right. Right. Though I have not done yet, but then that's the trends, I think. Yeah. Yeah. Questions? Okay. So maybe today is a bit basic lecture because of the time, and then I think I will stop here. And thanks very much for joining, and please enjoy the rest of the stay in Japan and Kyoto. Thank you. So I said that around 11:15 you have the long day today, so maybe take the 15 minutes break, and then Kodai Yamamoto will come here to give you lectures. Thanks.
So let me introduce myself first. So if you see the kanji, my name contains young mountain book. Whatever kanji, it means large and large. So I'm not actually human, but large mountain and large books. So I'm program specific assistant professor, and I obtained PhD in Kyoto University 2021 in the Department of Civil Engineering. My research interest is currently my research interest is climate change and land use change impact assessment on flooding. So as you see this. As you see this figure, this is the Earth. I'm sure you are familiar to climate change studies, but currently there are international framework to develop the Earth system models. The international community called IPCC is making a scenario to force this model to assess what if the CO2 in global is increased at the end of the century, what is the impact on the Earth, or temperature or precipitation. My interest is, so what if the global warming is progressing at the end of the future, what happened to flood, hydrology or flooding. So currently, my current focus is humid tropical area, which is particularly Indonesia. This is left figure is a picture of my picture in the field in Indonesia in February 2025. Maybe I think you are Indonesian, right? You know, I saw in the recent participants. I visited 2 or 3 times to the field in Indonesia, and I do field study as well as assessing the climate change or land use change impact at large scale using the hydrologic model. So, this is my research interest and work, but outside of research, I like to do watching movie, Netflix or Disney or whatever, or traveling abroad. Last year I visited Taiwan. I bought a lot of pineapple cake, a lot of instant noodle, and then a lot of mochi, kind of rice cake. Of course, I like to have a Taiwanese green tea, good coffee from Indonesian too. So yeah, this is me. Today, as I introduced, I will show a case study of a climate change impact assessment, which I did in my PhD time and ongoing study until now. So, as you may know that climate change and heavy rainfall have a relationship. This figure is a global map of the projected changes in annual maximum daily precipitation. So you see the 3 figures. Left figure shows that what is the global warming at the end of the century increased by 1.5 degrees. What happened to how much the annual maximum daily precipitation, like extreme precipitation, will be changed. As you see that if global warming is increased by 1.5, in most of the area, the heavy rainfall will increase. As global warming is higher by 2 or higher by 4, you can see that in most of the world, the extreme precipitation is increased. So my interest is then, this is annual maximum daily extreme precipitation. So it's a precipitation in one day is increasing in the future. What happened to flood all over the world? So, today, I would like to talk about 3 contents. First, to assess the climate change impact on the flooding, you need the model, the hydrological model, which can express a large river basin dynamics. So I'd like to give a talk about, I'd like you to understand the how to do hydrological modeling at a large scale river basin, taking a case study in Batanghari River Basin, Sumatra in Indonesia. Secondly, I'd like to show an example how to assess the climate change impact using hydrological model, how to handle the climate model output data, and then force the hydrological model. Finally, I will talk about further climate change impact assessment by showing how to assess the flood damage on agriculture in this humid tropical river basin. So first, maybe you heard about RRI model in the first lecture. Yes. So first, since my supervisor was Dr. Sayama, I was using the rainfall inundation model developed by Dr. Sayama and I would like to show how to apply to the large river basin, how to set up the parameter, and then so on. So this is a study site. As I mentioned repeatedly, this is Batanghari River Basin. It's kind of far from both Taiwan and Japan. Before I visited here, I didn't know this river basin, of course. So you see that Japan, this is a map in the Asian region, and this is Japan, and this is Philippines or Taiwan is around here. So Batanghari River Basin is located in Indonesia, which is nearby the tropical region, tropics. Batanghari River is located in this big island in Sumatra, big island called Sumatra Island, Indonesia. If you want to know further, maybe you can ask personally to him later on. This river basin is quite big. It's 42 square kilometer. If you are not hydrologist, it may be hard to imagine how big it is. So Japan's largest river basin is Tone River Basin in Tokyo. It's about 10 square kilometers square. So this river basin is 4 times as large as Japanese largest river basin. There are 24 rain gauging stations. It's kind of limited rain gauge station to understand how much discharge is, how much water is flowing at the downstream. So it's considered as a limited gauging station for large river. And there's one gauging station for measuring the river flow or river discharge, as shown here. Unlike the developed countries, there's annual flooding because there's no levees or river bank systems are not developed here, or rivers are more in natural state. So this part is capital of the Jambi province, which is in Batanghari River Basin. And you see there are a lot of, it's urbanized area, and in wet season there is a flood event here in Jambi city. This is kind of the annual or seasonal event which happens every 2 years or 3 years or 5 years. Then this humid tropical river basin, or let's say the river basin in Indonesia, is kind of unique. For hydrologists, it's important to understand the soil characteristic, soil physical characteristic, so that you can know how much rainfall can enter the soil and how much soil can store, or how much how fast water will flow on the slope. So if you look at the right figure, you can see that this is a hill slope, like 30-meter hill slope and 12-meter height and 30-meter length hill slope in Japan, forest in Kiru experimental site Shiga in Japan. If you measure the soil depth, if you dig the soil, you can easily find out the very hard part, bedrock. It's usually the soil layer is just 1 meter. So rainfall is entering to the soil, and water is moving up and down or flowing within 1 meter of the soil. If you dig more than 1 meter, you will easily find the bedrock or hard part of the soil. But I was going to the forest area in Sumatra, and I was digging the soil with Dr. Sayama with help of Indonesian researcher and villagers. And we found out that in Sumatra, the soil layer is quite thick. It can reach 3 meters or higher. So we kind of understand, based on this soil depth measurement, comparing with Japanese typical soil, we understand that this here, at least the soil depth is quite unique in Sumatra, in Indonesia, and it's much thicker than soil depth in Japan. So this is a research gap. Most of the we call rainfall runoff model, which is used for the hydrological model for climate change impact assessments or operational flood forecasting. Most of these rainfall runoff model is developed based on the observations and findings in the temperate regions, actually. But based on the observation and literature review by Kumagai, it seems that in tropical region, or particularly Indonesia, the soil is much thicker. So we are kind of assuming that the soil can store more water, and water is going slower than Japanese river basin. So we are curious to know the current rainfall runoff model developed by the finding of temperate region can be applied to this humid tropical river basin, which has quite unique soil. And we are exploring the application of rainfall runoff inundation model by changing the parameter and model structure. And then, secondly, we are applying this RI model because this river basin has limited rainfall gauge stations. So we were thinking to use satellite rainfall data and see how much satellite rainfall data and evapotranspiration data estimated by global reanalysis data can represent the river flow at the downstream using the physical-based hydrologic model. So maybe Dr. Sayama introduced this figure, but let me introduce simply this rainfall runoff inundation model. So this is quite practical model. If you have the rainfall data and topography data for digital elevation model, this model can simulate the discharge at any grid in a river basin, or water level, or inundation. For example, this is an upstream mountain, and this is a downstream rivers. You can simulate the discharge in this upstream or discharge at downstream, or river flooding at downstream. In addition to this model can represent the inland flooding due to the heavy rainfall. So how to set up this? So because the soil characteristic is unique, so how to set up this runoff generation in the slope? Otherwise, how to set up how water is moving in a mountainous soil. So in Ararai has a kind of default typical parameterization. It depends on the land cover type, as you see the right figure. So far, based on the finding of observation, we identify the 3 types of runoff generation. So in urbanized area, you can understand that the surface is covered by asphalt or concrete. So if rainfall happens, it doesn't go to the subsurface or underground. So we are assuming that if the land cover data shows urban area, hydrological modelers are assuming that the water flow happens only on the surface. And then there are 2 types of the runoff generation process depending on the how the land is steep or flat. So in flat area, you can imagine paddy field in flat area. You cannot imagine that water is flowing laterally, but water is more absorbing. Soil is absorbing water, and water is moving vertically. So in RRI models, in flat area, we assume that if you find the paddy field or crop land from the land cover data, we apply the vertical infiltration model. And then in a steep area, the observation shows that the water is going to the soil, and water in the soil is flowing laterally and moving to the downslope. From the land cover, simply saying that if you find the mountainous area, we assume that the mountainous area is equal, mountain or forest is growing in a steep area. So from this land cover, if you find the forest area, we apply the subsurface flow or lateral flow processes in the soil. So after we select the land generation based on the land cover type, we decide the parameter based on the measured value. So RRI has 12 parameter set depending on the soil type, and there is a global soil cover data. So if you click the soil cover data in your river basin, you can decide you can use the measured value of the parameter. So after selecting the land generation and deciding the parameter, we can already run the model, but we need to set up how much river, we need to estimate the river width and depth based on the measurement. So because RRI is initially developed for developing countries such as, or in unengaged river basin, such as Kabul River Basin in Pakistan, or the Thailand, Chao Phraya River Basin in Thailand, or Soro River Basin in Indonesia. So there's a function to estimate the river width and depth using the formula. And this formula is an exponential formula. There are two parameters, C and S, and another one is catchment area. So if you decide the two parameters, so depending on the catchment area, width can be estimated. Well, you can see this figure. So if your catchment area is 10,000 square meter, the width can be 5 meters if you decide the parameter like this based on the measurement value. So in this study, we measure the river width and depth at 11 locations, and then fit this function and estimate these parameters. So as I said, this river basin has limited rainfall gauge data. So we are planning to use the satellite rainfall data called the GS map. But you have to be careful about the satellite data because it has some error of rainfall quantity. So here, before we use satellite rainfall data to force hydrological model, we compare the annual rainfall based on the satellite for GS map and gauge station. And if you see the left figure, the gauge station is displayed by the points, and the background figure is the satellite rainfall data. You can see that in this area, the rainfalls, annual rainfalls are higher in western mountainous area. This is a mountainous area. And rainfall is higher in mountainous area and decreasing in the smaller in mid-river basin and much smaller in urban area. And if you see the gauge station, the if you see the satellite data, this annual rainfall special pattern is following the pattern of the gauge station well. Right figure is comparing the annual, comparing the mean monthly rainfall, basing average rainfall. The blue one is showing the monthly rainfall obtained from the satellite. Black dot line is monthly rainfall obtained from the gauge station. And if you compare it, you can see that the satellite is larger, overestimating the monthly rainfall compared to gauge station. But if you see the patterns of monthly rainfall, you can see that satellite is following the observation pattern well. So after that, we give the satellite rainfall to RRI model with given parameter river width and depth. We run the simulation and compare the river discharge with observation. Here, blue line shows simulated discharge and red line shows observed discharge. You can see that the model river discharge is very peaky from 2012 January until end of 2013 December. But you can see that it follows patterns, temporal pattern of discharge well. But this simulation is done by default setting of the temperature region, assuming that soil depth is 1 meter. The water flow on the slope is quite fast. So we kind of actually want to explore what if the soil depth is 3 meters, how much the model simulation changes. As you see that compared to the previous one, the peak flow here was reduced if you change the soil depth from 1 meter to 3 meters. So it means that water is more stored in the soil in the model. Peak discharge was reduced in the river. But as you see, that the low flow is still underestimated. That's kind of how to improve this status. Based on the observation or finding in this tropical hill slope, we found out that there are abundant groundwater existing here. So in this RRI model, there is groundwater. So we added the groundwater model to the existing RRI model structure. And then, as you see the slides, for example, in this slope, the low flow was, model simulates the low flow better and low flow performance was improved. So after setting up the unique 6 soil depths and introducing groundwater model to the RRI model, we finally compare the simulated result, which is shown by the blue color. We finally validate the flat inundation patterns in this river basin. And this is a flat inundation pattern in 2017, March 12th. And the pink one is satellite imagery data obtained from the Sentinel. Blue one shows flat depth distribution obtained from the RRI model. If you compare the model is covering the model and observation have similar special pattern of flat inundation, even though at some downstream, the model is showing more flat inundation compared to the satellite imagery. But this satellite imagery also has a limitation. In this downstream, part is covered by the dense crest or canopy. Satellite, this sentinel cannot penetrate cannot capture the water under the canopy. So, for example, here, if canopy is very dense, the satellite may miss some flood inundation. So, but of course, the model have room to improve. So, but at this stages, with given the satellite rainfall and given the globally available soil data and land cover and the given parameter, you can see that the RRI model performance for flood inundation is not so bad compared to observation. At least it's not so unrealistic. So from this study, I would like to tell 3 take-home messages. So one is that this research was investigating applicability of RRI model in a humid tropical river basin, try to represent the unique 6 soil depths and groundwater component. Then this research identifies that the unique soil depths and groundwater will improve the low flow and high flow of the river discharge in this river basin. So next, I would like to move to climate change assessment on flood and inundation. I was wondering, are you familiar to climate change issues, or do you learn it in the class, or do you do this kind of research?
SDGs research.
Okay. So you are familiar to climate change? Okay. So in this DPRI, there are a lot of the researchers who is doing research about climate change from the understanding mechanism of climate change, why the weather system change if temperature increase, to my research like what is the impact of climate change on floods. So as I mentioned, the climate change is simulated by GCM, or General Circulation Model. And here, one of the GCM called Atmospheric General Circulation Model, its AGCM, was used in the study. So to assess the climate change impact from the Earth system model, you need to decide the scenarios in the future. And in this study, we use the RCP 8.5 scenario, which is equivalent to the 4-degree increase by the end of the 21st century. So we use the highest scenario to force the AGCM. But some AGCM some AGCM fail to represent the regional climate. So in this study, we further downscale the general circulation model output in this domain covering the Indonesia. So by dynamically downscaling, so HCM is originally covering the Earth, simulating the climate with a 20-kilometer resolution. By dynamically downscaling, we can get the rainfall outputs with a 5-kilometer resolution. Then after that, we did bias correction of rainfall outputs and force the RI model. So first, with a given parameter, we are making sure that the model performance on the monthly discharge is from 2001 to 2013. So we confirm that the orange one is a model simulation, and black line shows the observation. Black one shows the model simulation, and orange one shows orange one shows model simulation, and black one shows observation, and we confirm that model performance is not so bad. And after that, we did two bias correction. We tried two bias correction methods. Sorry, this is very unstable. Okay. So, yeah, this is very technical part of bias correction, but currently there are many researchers who is dealing the climate model outputs, but assumption of bias correction that any GCM has some biases compared to observed output. For example, the GCM rainfall is underestimate or overestimate compared to observation. So there is a technique to correct such a biases of the general circulation model. In this study, I used the bias correction method to correct the rainfall with daily rainfall from low to the high, with low to the high. We estimate the cumulative distribution. We construct the cumulative distribution function using basin average rainfall from climate model output. And we shift it. We make the bias correction factor at each return periods. And then at the same return period, we apply the same bias correction factor to the future climate model. So by doing that, at any return period of daily rainfall, we can correct the biases of climate model in the present climate and future climate model. So we did two kind of bias correction method. One is to correct the basin kind of mean rainfall over the study area, which is called the QM. And another one is the bias correction method to correct mean rainfall and special variability of rainfall. This QM correction of mean rainfall is quite popular method, and you can find it in the previous study. So after I apply the bias correction method, as you see that this is annual maximum cumulative rainfall for daily in the left figure and 15 days in the right figure. And original model shows a gray line of cumulative distribution function. After bias correction, it's shifted to up. This observation is shown by the orange one, and model is showing the gray one, and this is present climate. So you can see that there is a gap between observation and model. And after bias correction, model outputs was corrected, but corrected model outputs are shown by the orange line, and you can see that the biases of the original model was corrected and are comparable to the observation. So here we kind of investigate the impact of these two methods of bias correction, but we finally concluded that if we correct the mean rainfall over the domain and special variability of rainfall over the domain, we can correct the not only the mean rainfall over the domain, but special pattern of the rainfall. So here, after we collect the rainfall, we force the hydrological model under the present climate and under the future climate. And left figure is showing the average flood inundation extent in the current climate, and right figure shows the flood inundation extent under the RCP 8.5. So what if the global warming increased by, global temperature is increased by 4 degrees? So you can see that the flood inundation in the downstream was quite enhanced by the climate change. Specifically, the maximum flood inundation depth is increased from 3.7 to 4.8. Inundation area is increased by from 1,391 square meter to 3,203 kilometer square. So inundation extent is almost triple because of the climate change. So here take-home message is that first I applied the bias correction method to correct the mean rainfall over the domain, but it failed to represent the special pattern of the rainfall. Then I introduced, I corrected not only mean rainfall over the study area, but also special variability of rainfall. And then after correcting the biases of the regional climate model, this study assessed the future climate change impact on flood inundation, and we found out that the flood inundation extent is increased by 3.3 times under the RCP 8.5, which is the worst scenario of the climate change. And then we further assess the damage of this flood to agriculture, because this area is dominant. In this area, dominant land cover is agriculture. So well, so left figure shows so we are assessing the future so flood inundation is increased by 3.3 times. Then what is the impact to the people or agriculture area? Typical study, as I did, assess only climate change impact to rainfall, then how much this future rainfall will change the flooding. Or if you want to assess the land cover change, how much this land cover or land use change. For example, if catchment is urbanized, how much the urbanization impact to the discharge using the hydrological model. But what is lacking in current study is that sometimes if flood happens, it impacts to the special pattern of land use change. For example, in this area specifically, when the flooding is happening, so often, sometimes farmers are giving up the land or shifting the agriculture area from inundation nearby the river to more upland slope. And this kind of interaction between flood and people are not considered in the climate change impact study so far. So in this study, we try to consider this interaction for the damage assessment of climate change. In addition to this, so agriculture area is not only shifted by the disaster, but also changes because of the market price or socio-economic condition. Maybe it's easy to imagine it's related to daily life. So how to estimate the future agriculture is one of the challenging. There is a global data of the future socio-economic, it's called SSP scenario, shared socio-economic pathway. And it's usually used to estimate the future rainfall, but some researchers are making the future land use change under this future socio-economic scenarios. So this study is estimating the future agriculture area using this future socio-economic scenario, and then to estimate the future agriculture lands, we consider how the people respond against the flooding in the modeling. So yeah, this slide shows just what I said. This study tried to estimate the future agriculture area using future socio-economic development scenarios. Try to use a future flood as a limiting factor for the farmer. For example, if flood happen in particular land severely, the farmers cannot use the land. We try to represent using the model. Particularly, as some may know, the oil palm plantation is kind of dominant agriculture in this river basin. As you see the top figure, Indonesia is the country which produces the most oil palm plantation. So we developed the two socio-economic scenarios to estimate the oil palm. One is a business as usual scenario, and the other is a sustainable scenario. And in business as usual scenario, we assume that the technology to improve the crop yield or crop growth will not change in the future. So in this area, oil palm demands are increasing. So if oil palm demands are increasing, because technology is not improving, oil palm plantation area is increasing. That is a business as usual scenario. And another scenario is sustainable path scenario. We assume that in the future, the agricultural technologies are much improved. So in a small area, you can get the high yield of oil palm. So after we make this scenario, we estimate the future oil palm demand in this river basin. Sorry, time is limited, so I will just simply explain. So red one shows so this red line shows oil palm demand in this Batanha River basin. Because it's sustainable, it's because in this business as usual scenario, agricultural technologies are not improved. So demands are increasing. Agriculture area in this river basin are increasing. But in 2015, according to literature, the population growth will stop in this area. So people does not need more oil palm. So we assume that after 2015, oil palm demands are constant, then oil palm area are constant. Green line shows oil palm area required in Batanha River basin under sustainable scenario. And you can see that up to 2020, oil palm are increasing because demands are increasing. But after 2020, up to 2100, even though oil palm global demands are increasing, but technologies to grow the oil palm and get the higher yield in smaller land is agriculture technology is much improved. You need a much smaller area to grow the oil palm area. So we use a land use model called a CRU model which is open source and available and developed by Baba and Obama. And we give an input of this oil palm area under the sustainable pathways and business as usual scenario, and then simulate the future special pattern of the land cover, including oil palm. And here the left top shows the satellite imagery land use estimated by, sorry, let me extend 5 minutes up to 5:12. So the left top shows the land use and land cover data based on the satellite, and red color shows the oil palm area. And you can see that the oil palms are located nearby the forest in upstream, and as well as mid area and lowland area as well. And under the B shows the sustainable path scenario. And you can see that oil palm area is much reduced under the sustainable scenario because the technology is improved. You need a smaller land to grow the oil palm. So if you see the special map, oil palm area is much reduced. Especially you can see that oil palm area is shifted from lowland to upland.
Because there is a lot of growth.
Yes, because this land use is also considering the future flooding as a driving factor to decide the land use. Thank you for your comment. Under the business as usual scenario on the right top, in 2100, you can see that there are many oil palm in this river basin because global demand of oil palm is increased, then technology doesn't improve, so area is expanding. And you can see that especially oil palm are expanding around the current oil palm area, including the downstream area. And left three figures shows the flood extent. Left down figure shows the flood extent under the current climate condition. And right two figure, medium figure and right figure shows the flood extent under the future scenario. If you compare, if you compare this flood extent and land use data, you can easily see that under the future climates, first under the future climate, flood inundation are increasing, especially in downstream, and under the sustainable pathway, because oil palm are reducing in the downstream and shifted to upstream. You can see that the future in sustainable pathways, the flood damage is less. On the other hand, in the business as usual scenario, if you're focusing on the downstream area, the oil palm is increasing in downstream area, even though our model using the future flood as a limiting factor. So in this scenario, unfortunately, the flood damage due to climate change, flood damage to oil palm due to climate change is increasing. And this is the only downstream picture of the land use cover and the flood extent. You can confirm that the flood is increasing in the downstream. If you see this flood extent area in the future, how much oil palm are located in this flood area, you can easily see, because we use the same flood data, you can see that under the sustainable scenario, the oil palms have received less damage compared in sustainable path compared to damages in business as usual scenario. This is final take-home messages. So this study demonstrates the projected changes in flood damages to oil palm plantation and SSP under the sustainable pathways and business as usual scenario. Considering how future land use change is affected by the future flood. As you see, this SSP3 is a business as usual scenario. Demonstrates that oil palm area will increase in lowland. And because flood is also increasing in lowland, so future flood damage to oil palm is increasing. Even though in this model, if there is a flooding, the farmers hesitate to plant the oil palm. But in sustainable scenario, since the unsustainable scenario, which is called SSP1, demonstrates that oil palm area will decrease in peatland, and then the future flood damages are smaller compared to the business as usual scenario. Yeah, this is a final take-home message for this study. One of the reasons why I introduced this study is that current research trend is one of current research trend to assess the flood damage is how to consider the people response to flood. So not only how the rainfall are impacting or damaging to people, but current climate model impact studies consider how people are responding to flooding automatically. So yeah, this is a final take-home message. Thank you for your patience for my poor English and a long lecture. Thank you very much. If you want to ask any question, please visit me next room or just contact me by email or just talk to me. Thank you very much.
Okay, shall we start today's my lecture? In the beginning, I would like to introduce myself. My name is Wu Yinxin. I'm originally from Taiwan, and I'm currently working here. Today, I will give you. I'm very happy to have this opportunity to present my recent research output. I would like to talk about numerical modeling of transient water table in shallow, unconfined aquifer. This topic is related to numerical modeling of groundwater flow. So, does anyone do groundwater flow modeling for your research here?
Not yet, but I need the specific research.
Okay, you are kind of determining your future research now.
Probably because
okay.
I need the groundwater management also.
Oh, okay, good. Okay, so maybe I can, but in my talk I will not talk about the so-called traditional technique of groundwater modeling. Instead, I would like to introduce a new method, a new theory, recently I developed. Okay, so hopefully I can finish that in 1 hour. In the beginning, I would like to, my original research background is landslide and then debris flow. Does anyone do landslide research flow? Debris flow? Okay. Thank you, Professor Lee. As we know, there are 4 kinds of so-called generally landslide phenomena. First one is so-called deep city landslide. So the value depth is quite deeper, more than 10 meters or more deeper. For example, the Xiaoli Village in Kaohsiung, 2009. So it's one type of landslide. And another one is very famous, so-called rainfall triggered shallow landslide. This site is in Hiroshima. Usually the value depth is just about 1 or 2 meters or more or less. And if the value mass mixes water and transport to a long distance, we call it the debris flow phenomena. And finally is that if the water is more, for example, if the rain brought much water, and this water mixed with all the sediment and the soil rocks, and we can call it the so-called hyper-concentrated sediment flood. So these four type of, so we usually categorize as landslide or sediment disaster, and they are very common type in Japan. In my research, I would like to know the source, how much soil and rocks generated on here slope. So I would like to do, in my research topic, I'm trying to develop the so-called landslide model to estimate the occurrence, location, and the distribution. So very important thing is the groundwater. Why is this important? Let me use this photo. This site, the photo was taken in Hiroshima Prefecture. I went there. Okay, so here you can see this disaster happened in 2014, and this disaster caused more than 80% died. Specifically, you can see here the debris flow impact the community and also another house here, and this disaster caused more than 80 people died. So it's quite very important. And I went there, go climb the mountain to the source area to see what happened there. And this is the photo. And we can see that in the source area, on here slope, we can see this very fresh bedrock. And also above the bedrock, we can see this thin soil layer. And also above this thin soil layer, we can see very dense forest, or so-called vegetation. You can see also here, you can see the vegetation here. And within this layer, for example, in this case, the depth of this soil layer is about 1 and 1 point high, and we can expect, we can imagine that when the rainfall comes to this place and fall down the ground, and the rainfall infiltrated inside the soil layer, and the water will infiltrate it until the bedrock and accumulated on the bottom of the soil layer. In the case, when saturated zone, which means filled with water in this soil layer, and this saturated zone will trigger the landslide. So this in my model, I would like to model this so-called saturated zone, the surface of the saturated zone, also called water table. Okay, so this is the parameterization of my model, and we can Okay, so because I'm doing the model, so I would like to, I need to define the parameterization. So in my problem, as I show you in this photo here, so I'm considered quite a bedrock, and also above the bedrock there is a soil layer, a thin soil layer, so-called thin soil layer. And we can find that because the depth of the soil layer is quite shallow, but the propagation distance is longer here, for example here. So this is a very typical soil layer on here slope. And I try to model the water table in this kind of soil layer. So in my parameterization, you can see that as I mentioned, that the longitudinal distance, the scales is we define as a big L, and the depth of the soil layer, or so-called this boundary is water table, and the depth of this water table, the height, the scale we define is big H. And because this is a very shallow soil layer, so we can assume that the characteristic scale of the depth to length is this parameter. It's quite small parameter. And then in my problem, I consider input of rainfall, so-called short-term rainfall. The time scale is about several hours. And vegetation, as you can see from this photo, the vegetation is also important above the hill slope in the field. However, in my problem, I can in my model, I can just keep it the so-called canopy intersection parameter here to just kind of estimate how much volume of the water will fall down. Because as we know that the vegetation, water or rainfall will be intercepted by the leaf or by the tree. So not all rainfall will go on the ground. So I can keep the ratio here. And then for soil layer, I simply assume the isotopic and homogeneous soil, which means that I don't. Even we can see that in the field, we can see a lot of rock debris here, and also different soil, different sand. Actually, the real soil there, it is a homogeneous soil there. However, for the simplicity, because I'm trying to do in the modeling, so I just assume they are homogeneous and isotropic so material this time. And okay, so there is another important problem, important setting that capillarity is not considered in my model. When in your graduate course of hydrology, you must learn the infiltration process, right? Infiltration process, soil infiltration process. OK 那个水文的陆渗运动，你们有学过吧？对不对？那陆渗里面会讲到非饱和的问题嘛？那非饱和里面呢，就会有这个表面张力的问题。OK， 但我这个地方我不考虑。Okay, so let me repeat English that if you try to study the soil infiltration process, you are trying to consider the unsaturated part of groundwater in soil. And in this unsaturated zone, the capillarity is important thing because the pore of soil is very small. So you can, this is a so-called effect of surface tension. When the water put inside this very small pore, and then due to the surface tension, you can kind of see the water is lit up by a height. This is so-called the capillarity effect. But in my model, I just try, because I try to model the water table, so I just assume that the water table is a very clear boundary here, and then the capillarity effect is not considered this time. Okay, so as I have mentioned the soil infiltration process, we have to consider two things. When the water falls on this hill slope, so can you tell me what kind of process will happen? One is a vertically infiltrated process, and the second one is a longitudinal, so-called transverse propagation. Right? Can you catch me?
Yes.
So when the rainfall falls down the surface, so in the beginning the water will infiltrate into the soil, and then go to the bottom of the soil layer and accumulate it like this way. But because this bedrock is inclined bedrock, so all the groundwater will flow along the groundwater bedrock to this direction. So we have two different propagation directions. So I have to estimate. First of all, here I would like to know what is the time scale of the two propagation. So as I said that, for example, commonly use this green method to estimate soil infiltration, and this is the we can roughly estimate the infiltration time scale using this formula. And for this horizontal propagation process, sorry, which means that the groundwater flow along the bedrock, we can basically use this formula to estimate propagation time. And then we can consider different soil type here. So for example, the sand, loam, and clay. So let me check which one for sand, loam, clay, which one the grain size is closer. Can you answer me? Clay or rock or sand? Which grain size is larger? Which one is larger? Okay, okay. Right? Can you?
large
larger
sand.
对，这个是沙嘛，然后这个是那个粘土嘛，
粘土
哪一个比较密、比较细？粘土嘛，对不对？对，上面是沙子比较粗。So okay, based on these grain size differences, we can kind of image the infiltration time and also propagation time. So here, I just try to compare the two time scale. So this is a vertical infiltration time over the propagation time. The formula is here, and we can put all parameter inside, and we can get this result. This means that if the parameter is small, which means that the time scale for infiltration is much less smaller than the propagation time. Okay, can you catch me this one here, where the parameter is small? Because I try to compare the two time scale, the infiltration time scale over the propagation time scale. And if the parameter is very small, which means the infiltration time is very small compared to the propagation time. Okay, so this means that if we try to consider we try to focus on propagation motion, the infiltration motion can be neglected. Do you agree?
Negative.
No, I mean you can ignore the because you are right now you consider motion in a longer time scale. So the very short time scale process you cannot discuss. So
the infiltration will be ignored.
yes, yeah, that roughly in modeling we can do this way. For example, like because the propagation of time, the characteristic of propagation of time, for example, is 1 hour, but the infiltration time is just several minutes or less than 1 minute. So if you try to focus on this hourly motion, can you see the 1 minute motion, several minute motion? You cannot feel that. This is a kind of relative time scale comparison. Are you okay? For example, like let me use different. Yeah, this is at the scale estimation. This is problem. Like for example, if you see I'm not sure if this is good or not. Example. For example, you can see a person, and if you just meet a person, maybe 1 year after 1 year, you can see the dramatic change. But within maybe the several days, for example, the growth of your hair, you cannot feel that.
Yeah.
Can you catch up this point?
Yeah.
Okay, thank you.
So if the time that requires is very big, you
Yeah.
can see the difference. However, if you put the time in a very short time,
Yeah.
the difference is not that visible, so you can ignore this implementation time.
Maybe inverse. For example, the infiltration time is kind of a very shorter time. The motion in the shorter time period relative to the propagation time. So right now, if you try to focus on the propagation time, then the infiltration process is you can safely, reasonably ignore.
Okay.
Okay. But you can think of this kind of scale estimation. Okay, so in this case, here just tell this slide. Just want to tell you that because I try to model the water table, or which means the propagation motion, so the infiltration motion here can be kind of safely ignored in my problem. Yeah. Okay, so based on the privatization here should list all the formulation. So for the governing equation, that's very common. What is this governing equation? It's a very common governing equation in the fluid mechanics. Continuity, mass of continuity, mass of conservation. This one. And the second one is so-called momentum equation. This deals with momentum change, also called velocity change. And for the groundwater flow, which law is very famous? Darcy's law. 达西定律，有听过吗？有听过举手。Raise your hand if you heard this law. Okay, so but for the traditional Darcy's law is only the part highlighted by the green box. This one is so-called Darcy's law, which means the Darcy's CPG velocity proportional to this is the hydraulic gradient. However, in my model, I try to introduce a so-called inertial effect here. Because I'm trying to use the REV scale. REV is so-called representative element, representative element balance scale. I don't conceive, for example, this is if you consider this is soil, this is defined as a REV unit. So this is soil, and the water will flow through all this flow here. I don't consider the very small motion. I consider the average property of this unit volume. So we can call it this is an REV scale problem. And the Darcy's law is usually used for this problem, this kind of scale. And here I'm trying to introduce the inertial effect, and later I will explain why I do this. And then on the groundwater water table, I impose the dynamic boundary condition, which means that the atmospheric barometric pressure, or we can say that atmospheric pressure is zero on the surface. And also on the bottom of on the bedrock and also the surface, we can impose to a kinematic boundary condition. The upper one is on the surface, and the lower one is for the boundary on the bedrock. So that's all formulation in my model. And after we have formulation, we have to do normalization to see which term is important or not. Because we don't have this kind of resources to calculate every term. We have to try to distinguish which term is more important. So here is all the normalization variable here. For example, the xy is the coordinate in the horizontal direction, and z and h is vertical direction. This h is depth of the water table. And UV are the Darcy CPG velocity in the horizontal direction, and the W is in the vertical direction. And the P is the pressure, and the time here, because I'm considered a problem on pier slope, so we have a so-called the here slope, there is a bedrock below the soil layer. So we have to consider the absolute longitude, altitude, 绝对的高度，对，绝对高层，对，就是如果我只考虑一层图层的话，那我只要讨论深度嘛。可是如果今天是一个斜的图层的话，那其实从底部上来还有一个高度，然后再加上那个地下水位的高度，所以是这个 zeta e， 有吗？Okay, so I described that because our problem focuses on the groundwater table in soil layer. So when the soil layer is mantled on the hill slope, so we must also need to consider the elevation of the hill slope. So this will generate another variable here. Okay, so then we put every non-normalized variable into our formulation, and after a lot of algebraic manipulation, finally we can come to this formula. And here I just put this tau here. Tau is the so-called realization time. And the meaning, the meaning. So the meaning of this realization time, I just would like to try to physically explain that. The physical meaning is that this means that if you ignore this term, then this is the original Darcy's law. And if you consider this one, you can, for example, when the flow inside soil is kind of faster, but the groundwater flow inside the soil, and that term with the mark in blue color with the realization time parameter means the kind of a small change of this flow. But because the time scale is very short, so if you try to see this volume, then that terms will be balanced and then go to the so-called equilibrium situation. So that's why I just put this small time scale here. Later I will show you the scale as mentioned. And for other formula, we can put all the normalization variable inside our formula, and we can finally conclude this formulation. And this tau is the normalized rainfall recharge. As I said, I ignore the infiltration process. So when the rainfall falls on the soil there, but we ignore this process, but we can estimate how much water will accumulate on the groundwater surface. And this term is rainfall recharge. Okay, so as we have the formula, and here I just roughly pick up several soil types and then put into the formula I just showed in the last slide. And we can see that the realization time scale here is quite small. For the annual gravel is the grain size is quite big. So we can imagine that the water is very easy to flow inside between the annual gravel. But for clay, because the grain size is very fine, so water is very difficult to flow through. So based on this property, the realization time scale for the annual gravel is 10 to power of -2, 0.01. But for the clay, it's quite very small, very small. So you can almost ignore all the distance, and then return to original Darcy's law. However, for this case, this is kind of this value is not so small, so we better to keep the two terms in our momentum equation, and that's the key of my methodology. Okay, so let me rearrange again the formulation. So for the mass conservation, we can finally conclude to this equation. And then for the momentum conservation equation, then we can get this one. So here I just remind you that because we can see this term here, because the tau is very small, so there is a very so-called a very steep source term. The meaning of steep source term is that this term is quite big because this parameter is small. Can you catch me? This parameter is small, so this must be very big. And if the source term is a big term, then this problem is so-called a steep formula. And the numerical model, the numerical methodology, the numerical modeling of this kind of equation is quite difficult. You have to do many, you have to apply several spatial treatment to deal with this term. Okay, so we have these two equations, mass conservation and momentum conservation. And then if we consider if the tau becomes zero, and we can combine these two terms and to get this one. And this equation is very classical and famous. We call it hydraulic groundwater theory. You can see you can study this equation from this hydrology Bible, authored by Professor Bussard from Cornell University. And in some other researchers, when you call it, this equation is a Dubin-Booth-Smith equation. Okay, so basically the theory I developed is kind of a more comprehensive version for this theory. Okay, so in this slide, I would like to tell you that what is the difficult part of the numerical model of my model. Let me use the example of the hydraulic groundwater theory here. You can see here, and these two terms marked by green, we so-called the nonlinear diffusion process. And these two terms usually dominate when the aquifer is placed in placed horizontally. So the diffusion process is very important. But if the soil layer is distributed on a very steep slope in this way, then these terms dominate over this term. So in these equations, we have two types of terms for different two types of propagation. For one for diffusion and another for advection. So why this is so important for us to solve that? Because we can use this example. Advection is kind of this way. Let me use one example, so-called the linear advection diffusion equation. So the advection process kind of, you can see this the wave and move with time. Move on the right side and in this way. So usually the wave will keep its form, but just shift the place as time evolves. So we'll go this way. However, for diffusion process is totally different. You can see that originally there is a wave here, and then this wave will infinitely spreading to both sides. So for the numerical, and then okay. So finally, if we combine the two, advection and diffusion, then we can get this result. So this wave and at this time step will go this way, will go to this location, and then the shape will kind of spread out. Okay, so for the numerical, classical numerical method for this process, we usually use the so-called explicit finite difference method with some initial condition. And for the diffusion, we usually use the implicit finite difference scheme. Most of them are totally different things. So when you try to do numerical model, and okay, so does anyone do numerical model for your research? Raise your hand.
The girls.
Okay, cool. So what kind of equation are you doing? 你在用什么？你在分析什么问题？
你们泡沫的。
那个什么水波方程式吗？潜水波方。哦，潜水波方程式。
OK， 哦。潜水波方程式其实就跟我这个，你看起来会有点类似，就是其实它是把潜水波方程式跟地下水把它合在一起，对。那潜水波方程式就是主要是这个部分啦，基本上没有对，所以那个做法就是就是我们用这种方式，就是显示的有限元素有限差分法，大概可以算。然后像我这个，等一下我会讲，我是用显示的有限体积法来做。对 ，OK。Right, so I just would like to use this slide to remind you that in my problems, there are two different kinds of propagation motion. One is the advection, another is diffusion. And for the advection, we have usually apply the explicit finite difference method. And for the diffusion, we usually apply the implicit finite difference scheme. And it's impossible to merge the two with one model. So I have to do some special treatment. Okay, so here let me directly jump to the my equation, my formulation. Okay, so let me use this form to introduce my formulation. This is called a one-dimensional hyperbolic system, and for this PQ, there are three variables. One is the flow depth, the groundwater depth. This is the Darcy seepage velocity. Here, just use a one-dimensional case. And then B is the bedrock. And this big F is so-called flux function, and you can just rearrange all the terms into this form. And this big S is the source term. And then if you try to do the partial derivative of to find out this is so-called the Jacobian matrix. We try to do the differentiation to this flux function with respect to all the variables here. We can get this form. And why I want to do this one, because this is the so-called hyperbolic system. And if you try to solve the hyperbolic system, you have to first of all obtain the Jacobian matrix, and then try to find out for example, in these problems, there are three so-called eigenvalue. You have to find out the three eigenvalue and eigenvector, and then you can successfully solve this hyperbolic system. 我这边中文直接讲一下，这重点是这样，就是因为我现在它是一个hyperbolic 是中文是我不知道，对不起。然后那因为我们比如说我们在解那个波的方程式的时候嘛，那我们要去把它的特征向量跟特征的特征值把它找出来，因为它其实就是它这个问题其实就是你沿着一条线。这个其实是在一个数学空间中，它是一条线。然后呢，你要解它的时候，你会得到它的在那条线的每个点的3个向量。那这3个向量呢，就是从这里来的。就你只要把这个东西可以定义的把这些东西直接代数找出来的话，你这个所谓的 hyperbolic 的方程式，你就可以把它解出来。所以我的做法就是把它全部导出来，然后那全部得到的结果就是这个样子。然后我可以得到3个特征值这边，然后它特征值相对应的特征向量就是这3个。那所以就是说这个问题呢，如果我要解它的话，那我现在只要能够把这个特征值先把它算出来，然后它跟着的特征向量我也把它算出来，那这个运动呢，在每个格点上的运动呢，都会符合都会由这三个特征向量去组成，那我这个问题就可以解出来。Okay, so is there any question? Then okay, just kind of
I use dashes lower minus pencil, but I'm using points, not the dashes. It's too complicated to use as simulations.
No, if you can use dashes, that's
So if you can
you
use
can do it. Yeah, you already do the most difficult part. One. Yeah. Okay, so anyway, I just try to tell you that in my formulation, I just propose this formula, and then right now I try to explain what I do to solve this equation. And this is hyperbolic equation, so this is a common practice to derive all the eigenvalue and eigenvector. Okay, so next one is that then as we already have the solution analytical part of the solution, then we start to talk about the numerical part. So here I'm trying to use because it's a hyperbolic equation, so I try to solve it using the final value method. And there are many different final value methods. So here I choose to use so-called wave propagation algorithm here. The formulation, you can see that is one. Basically, distance means the vehicle journey.
没有，还是要开冷气。
真的、老师觉得很
他切掉，他自己切掉。
OK，大家4个小时想说，我讲的内容老师觉得寂寞的，那我赶快把它解释。Okay, so let me go back to the formulation. And distance means the inflow outflow. Because we try to solve this equation, and basically this one is so-called a mass conservation equation. So distance is the inflow outflow terms. How much flow inside, how much flow outside can be determined by distance. And the next one is a so-called high resolution correction term. Because these terms we can only get the first order precision result. And if we were trying to try to get more the result in higher precision, we have to add this term here.
Feedback.
And then
Is it the feedback for the second order?
kind of, yeah. We can also, for some efficiency problem, we can ignore this one, but then the result will be very rough.
Yes.
Yeah. If the slope become more steeper or some changes much, there is a much big differences in our initial problem, then this term will give us not good result.
So, it's for the reducing the error from the equations. You add the feedback.
Okay, so I have to correct the ways. Let me correct that straight. Because we try to use numerical method to solve our problem. But numerical is kind of an approximation. We cannot exactly solve the problem, exactly solve our formulation.
Yes.
So in my method, the approximation, if I try to use this term to solve the approximation only gives us a first order precision.
Only first order?
First order. For example, like this is a very simple estimation. For numerical model, you will set up your delta S. For example, like 0.1 meter or delta T, like maybe 0.1 second, right? So if we instead of first order, so how much will be the error from this?
Not sure.
So, okay, so because we are setting up this delta S, so which means that we try to discretize our problem in this kind of size. So the error for the first order will be around maybe 0.01, maybe around this scale. So the error will be this kind of value. But this kind of value is very almost similar to this delta x. So we need to do need to add this high resolution correction. And if I add that terms, then the error maybe will become more small. So
More accurate.
yeah, under this precision, then we can kind of ignore error, right, in our numerical model. So this is high first order, second order. And in my problem, because I'm doing this kind of hyperbolic problem, so ideally when I'm doing this kind of calculation, for example, I'm trying to calculate the groundwater table depth in this cell. So in every time step, I try to estimate how much groundwater flow inside this cell or flow out. So let me try to simplify my my target calculation targets. I just basically try to estimate the value at this cell at this interface. So how much flow in, how much flow out at this interface. And if I can accurately estimate these two, the flowing flow out value at the two boundary, two interface, then I can accurately estimate the depth here. So how do I calculate the flow in flow out at one interface? So I'm trying to use this method, so-called F-wave method. And there are many explanations for these terms, but here let me just keep the times in time. So I will not say this very detailed, but basically this kind of this is a flux function. For example, at this interface, there are two flux functions here, flow in and flow out. And then resistance is so-called from the source term. For example, the rainfall recharge, or other terms for the relaxation process. And so all this here, the momentum, the flux in, flux out, and also the source terms. I use as I mentioned, the three eigenvector. I try to decompose the three eigenvector. Then we can accurately estimate the three eigenvector at each interface, which means that I can accurately estimate how much flow in, flow out. So this is the purpose here. Okay, so this is more detailed algebraic formulation for this one. So you can basically, if you can understand each one, then you can write the numerical program by yourself. Okay, so far the theoretical part is finished. Let me directly show you the result. Okay, so if I try to develop a numerical model, I have to compare with some analytical solution to see if my model is good or not, right? So here I'm trying to use this very famous classical problem of a so-called groundwater mark in many very famous textbook. So you can see that if this is the soil layer, and then there is groundwater in this shape, and then in the beginning just let the groundwater to freely flow inside the soil layer. So this groundwater mark will split out based on the groundwater physics. So my model try to compare with this analytical solution here. And later on I will show you the animation. And this one is a groundwater part, and the boundary is a bedrock, and this is the seepage velocity here, and this is opposite. Opposite means in this direction. This negative means that direction. So look at the screen to see the animation. And then the black dot. This black dot means the analytical solution. Directly solve this equation right here. So you can see that this groundwater mark symmetrically spread in two directions. And this is the seepage velocity, and 0 is in the center point. Okay, so this is so-called horizontal, the case for the horizontal aquifer. And what if we try to, as I said, I focus on the soil layer on here, so if I tilt up the soil layer here, then we can see this is a ground mark initial distribution. And also, we can do some, because I try to compare with the analytic solution, so I try to do some multiplication. Then this is the analytical solution for this problem, the groundwater mark on the inclined aquifer. So, can I start animation?
Cool.
So we can see this way. Well, the interesting part is that, for sure, this is go down 3. But here, that you can see that the groundwater mark go up first, and then the groundwater will continue until the one point, and there is not enough momentum to go up, so all groundwater will go down. So you can see initially go up and then go down. This kind of so-called direction change this problem is quite difficult, quite hard in the numerical model. And in my method, I don't have to do any additional way to manipulate this one. This model can compute everything physically by itself. Okay, so this is comparison with the analytical solution, and as I try to propose a numerical model, I have to tell you how good, how efficient of this model. And for elevation diffusion equation, we so-called a classical diffusion equation. So what kind of scheme is very famous? This one, the Kronecker method. Kronecker method is if you enroll in some in any numerical computation course, you have to learn this one, Kronecker method. This is a steady, unconditional, stable method for diffusion process. Okay, so let me show you the result. Like here is computation time here, and this is the grain size, number of grid size. So here is the grid size is smaller, and here is larger. So if you do numerical simulation and you increase your grid size, so what kind of change you will face? When you need more time or shorter time, if you increase your grid size. 如果你在做数值分析的时候，你把那个隔网解析度把它调小，那你隔网点变多的话，那你的计算会变长变短？变久，对不对 ？OK， 变久，对。Right, good answer. So I just would like to show you that if I increase the grid size, then how efficient is my model? And first of all, you can see that the Kronecker method basically is very time wasting. It took a lot of time, long time compared to my methodology. For example, if you try to see here, it's almost always different. Much difference is like 10 times or even more longer times. And also another thing is that you can see that this realization parameter, if the realization parameter is 10 to the power minus 2, then you will get a very efficient calculation. But if you start to make the parameter more smaller, you will get more longer computation time. So basically, I just would like to show you that my methodology is quite efficient than the classical Kronecker method. And this one, I want to use this slide to introduce the error estimation. If you try to verify your numerical model, what kind of error you would like to know? First of all, is error of mass conservation. If your model cannot keep the mass conserved, then your model will fail. So this is a very important issue. Then we can use this so-called first norm to check it. And then infinity norm here is just aiming to test the so-called local maxima error, which means that for example, if we got the numerical solution here, and then we for example, and this is the so-called analytical solution. If this is an analytical solution, and this is a numerical simulation, so you can see that there is a small error here, small error here, but there are some big error here, So the summation of all small error in this domain is so-called first norm. And for the very local maxima error is the infinity norm. So I use these two error estimation to show you that for the mass conservation, my model can keep the very good property of the mass conservation. But for the infinity, from the result of infinity norm, no, here. The local maxima error is not good here, particularly for the small, for the bigger realization parameters. We can see that. Okay, so here is a delta S. Usually as I told you that if your delta S becomes smaller, basically your result will be more correct because the space of the discretized space is smaller. Then your numerical solution will be more better. However, we will see that even this becomes smaller, but the error does not decrease. The reason is that because I'm trying to consider the problem with waiting from. What is a waiting from? For example, this is a bedrock, and this is the water table here. There is a boundary. This boundary is so-called a waiting from. For numerical method, this is very difficult to treat this boundary with or without groundwater. So the error comes from this place. So that's why the local maxima error will not does not decrease, because if the realization parameter is much bigger, then at the waiting from we need more treatment to keep the solution stable. But currently, in my model, I just cannot. I still have this problem, and I'm fixing this one. But for other realization parameters, we can get very good result. Basically, when the delta S becomes smaller, then the error becomes smaller. Okay. Then the next one is, as I mentioned, that the waiting from problem. So this result just show you the different green number. This is closer, this is finer. And this line is the simulation result of the waiting from the groundwater boundary. And the one circle is the analytical solution. And basically match very well. Just for maybe here, just a slightly very differences here. And this part is for the case of a horizontal aquifer, which means that the groundwater mass spread symmetrical. But this is inclined aquifer in this way, so the groundwater mass will go this way. Can you image that? On the inclined slope. So for the low part, the waiting from for the low part will go in this way, and for the upper part will go up shortly and then go down. Can you understand the image of the meaning of the figure? Okay, no problem. That's a directly see different case. So let me assume different. For example, in this kind of shape, and this is groundwater depth, and this is seepage velocity. And from here we can see that because the water table here is higher, so which means the hydraulic gradient is higher and lower. 水力坡度这里比较高，还是这里比较高？哪里比较高？左边嘛，对不对？这里对不对？对，没错。所以它一定水力坡度比较高，所以它会高的往低的流，所以它就往这里流。So because the water table here is higher than here, then the right side, so hydraulic gradient is leftwards, in the leftward direction. However, when the water table become very horizontal, go to horizontal, then the groundwater will not move. So we can see that the seepage velocity is reducing finally almost zero. Right, this is this one case. And the next one, what if currently the bedrock is flat bedrock. So what if I consider the very big bedrock? For example, this one. This let me put a wave inside, and then again we can see the result. because there is a change, there is a bedrock change, the inclination change, so you can see the dramatically the change of velocity here. And again, that it quickly moved to this low part and accumulated in this part, and then when the water table becomes flat, horizontal, then almost the movement slowed down, and then you can see almost zero seepage velocity here. Okay. And this one here, you can see a more clear wavy pattern here. And because this is a very steep, so you can see that the higher seepage velocity appear here. And the groundwater will separate it to the two parts, and this part will finally become stationary to stay here, and another one here. Okay, but let me stop animation. Otherwise, you will play to tomorrow. You will take a long time here. But here is a normalized time. Normalized time. As I say, I try to solve this equation using non-dimensional formulation. So this is normalized time. And yeah, this, let me stop the animation here. But you just keep the image that this my model can catch all these things directly. Okay, so far it's a one-dimensional case, and I can easily extend this to two-dimensional case. So two-dimensional formulation here, and it's almost similar to one-dimensional one, and just increasing another direction. So just have the image here, and let me show you the result here. Okay, so the result is that right now we consider a two-dimensional groundwater map problem, and this kind of there is a groundwater map here, and this is a bird view of this groundwater map. We see this on the just above the place, and the upper row shows the result of the horizontal aquifer, and the lower row shows the inclined aquifer, and the gray column is the elevation. So this is 10, which means that this is basically this is the slope like this one, and the top, the higher part is 10 meters, and here is 0 meter. So can you image this slope? Because the color here is the elevation.
Oh, so it's...
Yes, that way. Thank you. Good. Okay, so let me show you the and this is a simulation, and also this here is an analytical solution. So basically, you have to compare these two and compare these two. Can I start animation? Okay. Yeah. Alright. Yeah. So here you can see that the groundwater just spray symmetrically, but this one also at the back, a distant time along the slope. They match very well. Match very well. The point is that. Okay. So my methodology is successfully verified using analytical solution. For sure, if I can keep a very complicated topography, topography, and put the groundwater map on it, or any distribution of groundwater, then we can see how the groundwater flow on this topography myself. And so this is a two-dimensional problem verification using analytic solution. Okay, so today's a very quick lecture. I just introduced a new methodology to model the transient water table in unconfined isotropic homogeneous aquifer. And also this, in my nostalgia, I proposed a new hyperbolic theory using the so-called unsteady Darcy's law, and then a corresponding high-resolution final model well-balanced scheme. And as I show you the comparison between an unequal solution and this method is verified that it can successfully capture the waving front and also the physics. And finally, this methodology is implemented in the open source software, which means that it is a reproducible tool, and you can use it to try and for your study or for your research. Currently, the open science is quite important for our science community. We can develop tools and share with other people, and you can do more and more interesting research. Okay, so finally, this model has been published in the journal, so if you are interested, you can scan here, not here, to download the paper. Yeah, and then a lot of analytical part is branded in this paper. So if you find something strange or you can understand the content, you can contact me. You can do email at this email. Okay, so when you on your way go to the cafeteria, you see that there are a lot of trees in this campus, right? And actually in April, we have this kind of view in this campus. Yeah, it's a sakura cherry blossom season. So let me use this photo to wish you a pleasant visit in Kyoto University, in Kyoto. Okay, this is my today's lecture, and if you have any question or you want to know more, you please ask me.
Professor,
Hi.
are you you had a 1D simulation and 2D simulations, and are you challenging to have 3D simulations? So it's like the plane is like this.
In my model, actually this is kind of here, let me use this one. Oops, too much. Because as I explained that for the vertical infiltration process, the process is quite shorter than the propagation time, right? So the direction the motion in the vertical direction is kind of is not considered in this model. So this model is for the so-called two-dimension, but actually there is a depth there. So for three-dimension method, for sure this is okay, but it's not in this formulation. Yeah, I have to. That's a very good question. I'm trying to consider also the soil infiltration process using this kind of framework. So in that case, the three-dimensional model can be achieved. But for the current formulation, there's only two-dimensional model. Good. It seems you are interested in. No.
PhD. It's the two girls.
如果有什么问题，或者是有什么有兴趣的地方，或者是刚刚我讲的，你觉得我不知道我在讲什么，想要再多知道一点的话，你都随时都可以问，然后我可以尽我所能回答你们。
我先用中文讲，你们可能会比较知道。就是，你的老师之前有弄过土石流先端部的那个水的部分，因为先端部它是比较大的颗粒，所以它地下水它的水会不见。所以你有没有考虑过地下水在传输的过程中？因为其实地下水在陡坡的时候，它其实有时候会变成是一个流动层一样，但是它其实它不是水，它有时候是有点像混的浆，那看起来也在流动，但是它的 concentration 是有改变的。那这样会不会影响到你在做 spreading？ 因为你的 涛啊，就是你的阻力的部分应该是会存在，你会看起来运动会像是一个坡，而并不是像一个spreading 的，因为你是用那个动力波模式的方式下去做。
我确定一下，就是说老师您讲的意思是说，在土石流里面的地下那个里面的水，
先端部的水其实是被吸下去。
好，这个非常犀利，这个问题非常的困难。那我因为那原因是在说，如果你是做土石流问题的话，土石流里面的水含水量的问题的话，那它的地下水以外的固体颗粒的地方，它是在移动的，它是两边都在移动。所以在我的问题里面呢，其实因为我是假设是固体是不动的，那我只考虑地下水在里面的流动，所以应该是说，简单讲说它是一个静止的土层，然后里面的地下水运动的问题。所以现在这个方法的确是没办法解决刚刚林老师问的这个问题。那当然也这个是很有趣的事情，这也是我也很有兴趣的地方，因为其实土石流一直大家都想要能够物理的解释说那个流动的过程里面，它里面的那个颗粒的运动跟它的那个
对，但是
水层里面含水量的改变的运动。
In English is when the slope is sliding, the concentration of the water will affect the spread length. If it is concentration is low, the spreading will stop just near the toe of the mountain. But the concentration is high, when it goes underneath, it will spread longer. So in our handbook of landslide, the LO is different.
Yes,
it's similar, so
yes,
that's the reason I was considering.
Yes, that's a very interesting topic, and we are trying to explore this very difficult question. Yeah, but in my current model framework, I just consider the stationary solid. So which means that I only consider groundwater in stationary soil layer. So for the movement, that may be in the future if we can find some opportunity to challenge.
So can you use this equation in pollution spreading?
For sure, yeah. This model is basically for groundwater, and if I can immediately add one more concentration equation to join with the original groundwater motion part, and we can do the pollution propagation simulation. Yeah, that's no problem. Yeah, that's
some of our students are using the SWAT, SWAT model.
Yeah,
it can be used of underground water seepage and movement, and also use the like nutrition spreading, and also like if you have orchard tree on the top, not the nutrition but the pollution of irrigation, and also 肥料的传递那个以前李汉坑老师他们在讲那个污染扩散到水库的那个，他们就会做那个模拟现在是有一些是在跑2维，有些跑3维，3维就真的有点难，大部分是2维了，SWAT 是跑2维。
不过讲到这个有一个很有趣的问题是，就是说现在的污染有一些亲水性、亲油性的污染。就是那些东西其实是蛮不好听法，就是这种很难模拟，就是因为它是跟着你的里面的那个不见得是地下水，它可能是其他，比如说像有一些工厂，它有冲一些东西出来，那它的那个溶液是有亲油性、亲水性这些问题，所以它那个污染物呢是还有化学成分在里面。那以现在这个方法，它是单纯考虑水啦。但是我相信是可以把它增加那些化学的方程式进来，然后就可以去做那些分析。但是这个就是比较，我现在因为我讨论的是公塌嘛，公塌跟是地下水而已。
对，因为我们系上这几年在搞一个东西，就是像张老师在弄 的这件事情。那他们有平地的水的问题，然后我们是搞坡面的，那它会变成说有机，不是做封存，它是碳排放，意思是说我们 soil loss 里面它可能会带走有机质。有机质，但是这些有机质是靠地下水，或者是带着泥沙什么一起 spread out 的问题。那反而它其实是要知道是在一个历程，比方说一个降雨事件，或者是一个什么里面，我们这些的变化是如何？是这几年很多老师都有在碰的涉猎的部分了啊，只是说变成碳议题会想要知道那个时间多长，到底它带走的效益多少？
我不好意思，我确定一下，就是你是说比如说一场降雨，比如说豪大雨事件，然后
土壤的流失，
土壤充实，然后这充实过程又顺便把多少碳带走，或什么之类的这个技术。
就有人就弄这个，台大就有一批的人就在搞这个东西。
那个SWAT在那个美国农业部还有另外一个位。就是
WEP，
对，那个也是有人在用，对。
但那个好像也是跟我看它也会选有一点点有一些东西是相近的。
它刚才是传统的地下水马桶，
对，
然后它是可以做三维的。
三维，对。
哦，对，这些的确是很有趣的课题，但我比较我刚好着重的题目比较局限，所以就是其他这种比较高深的这种污染的传输的部分，我这边是还没有涉入。不过可以再额外增加方程式，这个东西是可以。
所以你都是把它那个土壤里面所有 homogeneous 的部分。
我先 homogeneous， 但其实理论上可以把它变成那个
distribution 的部分。那个上个礼拜那个Fujihara先生他们那边就有在把泥沙的，因为它是用 porous media。porous media 的在水灌入的时候，它的扩散的情况，刚好那个上礼拜那个有个有什么润一郎的竹内润一郎老师，他就做这个。
哦，好。
然后大家就听完那个 equation 就开始就出神了，这样。
它 porous media 的话，它的 scale 应该是 porous scale。这比我这个更小一点，那我是 RED 是整个平均，对。它如果是往里面看的话，那个方程式就很精彩。我现在的 unsteady dusty slope 其实是从这里出来的 ，pore scale 出来的。
对。
所以大家才会说，因为在这么小的 pore 里面，它在流的时候，它那个动能会比较明显。那所以就会有那个 emission。
然后那个屏科大的老师他们在做的是。就是它是在做透水沥青，那它是要让降雨的水快速的在不动的层里面赶快把水排掉，那让那个车子在
那个就是 LID 的问题了吧？
对，但是它里面就是要解决说，它有没有办法？这几年它是在弄的是降雨之后，把里面的细沙的部分有没有办法透过降雨把它冲掉？
对，把它塞在那里之后，就透水的能力就变差了。
对。
对，很多很高深的东西。
好，还没有问题？没有。
好，那我今天就先这样。如果有什么兴趣或什么的话，欢迎都可以，我刚的 email 可以跟我联络。
谢谢。
如果我可以回答你们的话。So you can contact me at my email if you are interested in any part, and I will try my best to answer you. Hopefully. Thank you. ちょっとお話しします。申し訳ないです。
それとも正解したことでいいか。
まあそうですね。ちょっと
じゃあ
专长，
施
工的专长，老师兼施工的专长。
这里没有，我可以跟我帮写的没有在。
Hello everyone. First of all, I would like to introduce myself briefly. My name is Yoshito Sunawara. I entered Kyoto University about 15 years ago, and I got PhD in 3 years ago. And my supervisor was Takahiro Sayama, who gave a presentation in late morning. So, and now I'm working as specially appointed assistant professor in DPRI. So nice to meet you. So today's topic is this title, analysis of compound hazard risk associated with climate change. So first is my background. So there are many types of natural hazards, for example, such as fluvial floods, storm surge, and some landslide, and other ice earthquakes. So many of these hazards are caused by severe weather conditions. So upper side is related in weather-related natural disaster. So therefore, natural hazards are strongly affected by climate change caused by global warming. So generally, these hazards become more severe by global warming. So in fact, particularly severe flooding has occurred over the past decade in Japan. These two photos is a very severe flooding photo occurred in Japan. So next is the what is the compound hazard? Recently, not only individual hazard, but also compound hazard is focused. This is due to mention of the dangers of compound hazard in the latest IPCC report. IPCC is the International Intergovernmental Panel on Climate Change, and AR6 is the latest report on global warming. This report is used in policy making in various countries, such as Japan and some countries. And there's no clear definition of a compound hazard, but here is one definition of I will show the one definition of compound hazard. Compound hazard is when multiple hazards occur, the damage becomes more severe than if each hazard had occurred independently. This is one definition of compound hazard. And this is one example of compound hazard in Japan. Last year, a strong earthquake struck the Noto region of Japan. In January, Noto region located in this red square area, and we are now located in Kyoto, this yellow box area. So in Noto region, a strong earthquake struck in last year in January, and followed by flooding caused by heavy rains in September. This compound hazard delayed recovery efforts. In response to this hazard, the national government is considering incorporating the weight of compound hazard into its response hazard policies. So this is another example of compound hazard. This type of compound hazard involved in multiple hazards caused by a single meteorological factor. So typhoons can cause heavy rain and high storm surge simultaneously, and both of these can raise river water levels. And if they occur simultaneously, they can cause the severe river flooding, such as this figure. In fact, Hurricane Harvey in the United States is recognized as one of such a compound hazard. Although such hazards have not been occurred in Japan, however, they may occur as global warming in progress. So now I would like to introduce our latest research topics related in compound hazard. One is the modeling approach. So our research group has developed the integrated hazard model that is called IHM. This one consists of some hazard model, and this model can simultaneously execute multiple hazard models such as the rainfall run model and storm surge model and landslide and sediment model. So this model executes simultaneously by using this IHM model. Through the exchange of variables, it enables the analysis of compound hazard that take into account complex interactions such as these many arrows described. And the other aspect is the data set. So since compound hazards are a combination of rare hazards, so sufficient analysis cannot be performed using only observation data. So here we use the large-scale ensemble climate data set. The Japan Meteorological Research Institute has released a simulation data set called D4PDF. This data set contains a large amount of meteorological data for each global warming scenario, such as present climate or 2K warming scenario, and other one is 4K warming scenario. By using this data, it is possible to quantitatively evaluate rare compound hazards. So this is one framework using IHM model. Now I'm working as a project. So this is framework for compound hazard for rainfall runoff and storm surge compound hazards. As I mentioned in previous slide, so in this framework, IHM executes rainfall run model and storm surge model, and forced by D4PDF climate dataset, and we will analyze compound hazard analysis. Okay. This is the explanation of element model of IHM. We will use the rainfall run inundation model as hydrological model. This model simulates the rainfall run process and inundation process simultaneously. The RRI model, this is model called by RRI model. This model divides the catchment into two-dimensional grids such as the aquaphenia and integrally solve runoff and inundation. In addition, our laboratory has developed the JRRI model. J means Japan. This model is targeted for Japan. This model divides the whole of Japan into these 14 regions and can simulate with 150 meter resolution, including small and medium-sized river basins, contains this area. And some model improvements have been proceeded, such as calibrating ground parameter according to soil type. And this is different element models explanation. We simulated storm surge by using advanced saturation model. This is called ADSAT. This model calculates the storm surge using wind speed and air pressure as driving forces. This model outputs the storm surge deviation in along the coastal line. And this coastal line's storm surge deviation is connected to this RRI model. This water level change by storm surge is applied to the RRI model's downstream boundary condition in the river mouth. So from this process, we can simulate the compound hazard by rainfall runoff and storm surge. This is the flow chart of the research analysis. So, to simulate compound hazard for tropical cyclone events extract from P4P dataset and reflect storm surge deviations output from ADSAT into the general river mass boundary condition, and to simulate peak water level in the 1,421 river basins by using GRI model in this area. So after that, we can see the effect of the compound effect, such as this figure. This figure shows the mechanism of compound hazard. Rainfall runoff, rainfall runoff drainage is blocked by storm surge water level deviation. This is the simulation setting and criteria. We set 3 experiments. So case RS means the with compound case, and case R and case S, case and case S represents the without compound effect. And this with compound and without compound result is compared, and we will calculate it, how much water level rise by compound effect, such as this figure. This figure is case R and case S is no compound case, but green one is compound case. In that case, is water level rise by compound effect. Such this difference is calculated in 1,421 river basins and 776 events. So we calculate this increase ratio. If increase rate over than 5%, that event we define the compound event as CE. And if CE is included so many events in there are so many events. There are so many CE events that river basin is we define compound river basins, which called CRB. This is river basins with a high proportion of CE, so likely to occur these types water level rise by compound effect. So this result shows the conditions that compound event occur. The green dot represents such a compound event I explained in previous slide. So, and horizontal axis and vertical axis is represents the case R and case S peak water level. This figure says that there is a correlation can be observed in each water levels. So storm surge case and rainfall runoff cases peak water level is correlated. This means that from this we can conclude that water level rise by compound effect occur when rainfall runoff and storm surge are similar magnitude. This means that this mechanism explained by this figure. So if storm surge is caused lower peak water level than rainfall runoff, in that case rainfall is drained to the sea. But if storm surge peak water level is similar to the rainfall runoff water level, in that case is rainwater is blocked by the storm surge. In that case is water level rises by compound effect is occurred. And this is the classification of the river basins. So all river basins is classified to the 3 types. Type R is rainfall runoff predominant river basins, and type S is storm surge predominant river basin. And type RS is both of them imbalance case. Important point in this slide is unexplained in the previous slide. CE compound event occurs when the scale of rainfall runoff and storm surge are similar. So type RS easily satisfied these conditions, and there are many CRB that are prone to the CE, such as type RS CRB is 50% of the type RS's all river basins, but other types is CRB's ratio is very low than the type RS. This is caused by the type RS is storm surge and rainfall runoff imbalance. From the previous result, we can identify the geographical distribution of river basins prone to compound hazards. This figure shows the distribution of each type of CRB. So it shows the high-risk area of compound hazards, such as the Seto Inland Sea. This area called Seto Inland Sea, and this area is called Ise Bay. They are the very high-risk area of compound hazard. And another aspect of this slide, so if under the similar conditions, so different trend can be observed, such as the Seto Inland Sea. Seto Inland Sea is a very similar climate condition, but in north side is high number of CRB, but south side is low number of CRB. So this difference is in effect of the river basin directions. So if river basin's direction is different, in that case is peak time of rainfall runoff is different. So in Seto Inland Sea, north side is peak time is correspond to the storm surge, but south side is very different trend of peak time of rainfall runoff. This causes this difference of the geographical distribution. This is one interesting point, this result. And this slide shows the where area is CRB will increase due to the global warming. So global warming is likely to cause an increase in CRB in the Kyushu region, red squared area. So this is due to the increase in typhoon intensity in the Kyushu region. This figure shows the increase of typhoon intensity. So the darker color indicate area where the typhoon will intensity. So Kyushu area is typhoon intensity become larger, and that is correspond to the additional CRB area this slide shows. And this slide, I omit the detailed explanation of this figure, but this figure shows change in flood frequency due to compound effect and global warming. This black line shows the present climate condition without compound effect. The greater decrease from this black line, such as this blue arrow, that means the more flooding will become more severe by compound or global warming. So green one is compound effect to the flood frequency. So blue one is global warming effect, and red one is both of them. So from this result indicates that both global warming and compound effect causes more severe flooding. And in addition, different types shows different trends. So in type R, which is the rainfall runoff is predominant river basins. In this type is the impact of global warming is significant. Such a blue one is very decreased the flood frequency, but red ones is a little bit decreased than type RS. So this means the global warming is predominant to the flood frequency change by global warming. But another, on the other hand, in type S, which is storm surges predominant river basin, the impact of global warming, blue one is little bit than type R, but compound effect is larger than type R. This is inversely result of type R and type S. This is the one different trend of the river basins types in compound effect and global warming. This is my research conclusion. So this research used the integrated hazard model and large ensemble climate dataset and simulate and quantitative assessment of compound hazards. So from these simulations, we obtained some results such as compound hazards are likely to occur in watershed where rainfall runoff and storm surge are in balance, type RS, and the effect of global warming are also strong. And we obtained geographical distribution of such a watershed. And these results will provide useful information for flood control planning and risk analysis. That's all. Thank you for listening.
有没有问题？要中文解释一下。
主要是做气候变迁降雨，
就是降雨啊，降雨之后径流跑到那个海边的交界口的时候，它的水位会回溯。所以主要应该是可能潮汐也有可能会有影响。Any questions? No. I ask. Due to the simulation, does tide height will affect like the lunar month? The tide is higher, and if the storm comes, will the effectiveness will be high?
Tide, you show
wave
the
tide.
astronomical tide.
Yeah.
So we don't consider the astronomical tide because astronomical tide is very important factor, but independent to the such a climate condition, because astronomical tide is caused by the moon's gravity.
Yeah.
So that to affect to the both of the good effect to bad effect if very low tide time, that is the storm surge become low, deviation is become lower, and if the high tide is become deviation is become larger and causes very bad effect. So that is the important to the flood control planning. So but this research mainly focused on the dependence of the two hazards, storm surge and rainfall runoff, caused by the one meteorological factor such as the tropical cyclone.
So the angle you mean, the last slide you mentioned the north and the south side. Yeah, this one. The type R and the type S, right? So how effectively will it affect the storm surge? If it's like the orange one is south. South means you're facing this way. right? Type S and type R is mean the north one, right?
No, type S means the high storm surge area.
Oh, high so
Yeah, such as these figures. So, such as this red one is very high maximum storm surge
yes.
in the data set. Such as this, deeper Bay Area is type S is located. And such as this rainfall ramp is predominant and storm surge don't
Effect.
that area is type S, R located. And type RS is balanced evaporation, such as this storm surge is strong, but weaker than this deeper Bay Area, such as this.
So what is the difference of the depth of the sea? You mean deep and shallow? What is the depth range?
Sorry.
The highest and the lowest,
storm surge.
海的那个是
高さは
高さこれですか？
は
3メーターがマキシマム。
that is the storm surge, but I mean in deeper sea, what is the effect? Deeper sea, how deep you define deep sea?
Deep sea.
Yeah. 就是它的深海跟浅海
它怎
的定义，
么定义深
海
是深海？
对。
它要定义深海或浅海。
对，因为它会影响到它的那个 red one 跟那个 green one，那个是 the red line and the green line is defined by the depth of the sea, right?
Yeah, deviation of the seawater level.
Oh,
So-
sea level. Oh, okay.
Yeah. 3 meters high from the 0 meter sea level to what storm surge.
因为我们台湾会有那个东部的海域的水深是比较深的，所以你很难在宜兰花莲造成回水的现象。但是我们在西部的话，因为台湾海峡很浅，所以它的回溯率是很高的。所以他现在说他的研究里面是不考虑那个涨潮退潮嘛，台湾每次都爆潮的时候就是直接回但是他不考虑嘛，他现在只有考虑的是，如果是在那个 Q50、100、Q2，然后如果说人家发生那个什么那个气候变迁的情况下，它到底回溯影响到底有多大这样子它的最 maxima 是3 meter，
3公尺。
The minima is maybe
那不是水，那不是海的深度。
不是，它是潮汐的那个深度。我只是说，因为他刚刚讲的是说the deeper sea because the seabed is much deeper, it will seize the surge, right?
Yeah, red one is higher than blue one.
Yes, but the sea depth, seabed will affect the sea surge.
Sorry, seepage.
Sea bed, B-E-D, bed. The
seepage.
bed, if the water is thick enough,
Oh.
the thicker it is, the smaller the tide wave will affect. In shallow water, the water is depth.
I see.
So when the storm comes, it's like a wall. So that's the reason that causes the storm ledge. But in deeper sea, it does not happen. So I think maybe it's related to your result. So I was asking that if what is the difference of the sea? If you define deeper section and the shallow section, what is the depth?
We don't consider the seabed height because we set the average seawater level in the Tokyo Bay is defined 0 meter sea level. And from that, we calculate the storm surge effect, how much water level rise from that 0 meter sea level to the.
So the maximum is 3 meters.
Yeah, from the 0 meter sea level in Japan.
他没有去说各个地方是多少。
So we don't consider the riverbed height, and this model will consider the surge effect.
所以它只给我考虑到水体的部分，
多少是相对的。
它没有考虑到溪床。那个。
We are running out of time, so thank you very much for listening. So next we will move to the DPRI museum.
So will we come back?
Yeah, we will not come back.
Not come back.
Yeah.
我被电脑，我到底在电脑看不到，是全部都要看。干嘛看？谢。
现在也是啊，这是
of the sun magnitude of the shocking. Oh, very large, huh? Yeah, let's try it very big. Oh.
京都方程研究所的小型博物馆，然后介绍各种的结果，摘的地盘的土沙摘，三方在这旁边也有立体地图，那这边也有立体地图，然后还有洲际半岛的。它底的说明，各种仪器的结果。然后我们上课常用的影片。
哦。